Hi.
Hello. Gotta go plug my computer.
Okay.
Hello.
How are you?
Pretty good.
Good. Hi. There's everybody. You guys ready for the weekend?
Did that code for we're gonna keep it short and sweet today, or what?
Yeah, actually.
Sounds good.
I don't think it's a lot to cover today. I should have made an assignment now that I think about it. I'll pull questions from somewhere. Do we have a new student, Aaron?
Timmy.
Yeah, we have a new student.
Reginald.
Well, welcome to the class.
I spit out my water, Andrew. Thanks.
I think we're missing one person. Who is that? Who are we missing? There, Skylar. All right, everybody's here. Well, I hope you guys had a good week. It's just about over. So for today, I wanted to go over, so like we've been doing problems with quantitative data. So like the heights of trees, the weights of fish, the weight of fruit, or the years, the lifespan of batteries or something. Data that's quantitative, that's more or less continuous. Things could last for 7.1 years. Things could weigh 10.1 pounds or something like that. It's made sense to find average values where we can take all of those numbers and add them up and divide by the number that we have and find an average that we call the mean. Does that make sense? And then we can find the standard deviation, which is kind of the average distance from the middle, the average distance from the mean. Sort of tells you, it sort of tells you how spread out your data is, in a way. Are you playing a game, Nate? Kinda. You look like it.
Nate.
He's just like looking up and his like mouth opens a little bit every once in a while.
I mean, I am talking to someone else, but
Oh, how nice of you.
yeah, I know.
Anyway, so that was, we can find a mean value with quantitative data, and we can find a standard deviation with quantitative data. With that stuff, we can build a normal distribution to model our distribution of data in a population. And then we could even create a sampling distribution from that, so that if we had a sample of size 10, we could make calculations on the probability of getting certain samples with a certain average, that sort of thing. Well, we haven't done a lot of that with the other type of data, categorical data. So categorical data is like, what color shirts is everybody wearing? I see a couple blue. Aaron's always got red usually, right? And then, and I'm always wearing gray pretty much, almost always. You can't find the average color of the shirt. Like there's no way to add up the colors and divide by how many people there are. So there is no average for color, but we can talk about the frequency or the percentage of people with blue on, or the percentage of people wearing gray. We can find what we call the proportion. And the proportion can sort of act like the mean for categorical data. When we build a normal distribution or a sampling distribution for categorical data, we treat the proportion, which is a percentage, as the mean. And then now, one thing to know is that a percentage as a decimal is, I'll try to look at the camera more. I suck at that. The percentage as a decimal is a number between 0 and 1. So like 90% would be 0.9, 50% would be 0.5, 11% would be 0.11. So that's one thing to note, is that it's just like a mean, but your mean value for the weight of fish could be like, I don't know, 3 pounds. It's bigger than 1. But a proportion is always between 0, representing 0%, and 1, representing 100%. So it's always as some decimal. Now so if we wanted to build a sample, so like, let's say we're in the situation where we want to know how, like, was it you, Nate, who had that giant bag of peanut butter M&Ms?
Box of goldfish? You mean this?
Didn't you have peanut butter M&Ms?
No, that's not me, Chief. I got goldfish. I got fins.
Well, who had the peanut butter M&Ms? I don't know. Anyway, let's say you did have, like, it was like this, like a bag for like a horse. It was like a big bag of peanut butter M&Ms. The different M&M types have different proportions according to the factory for the percentage of reds, the percentage of browns, the percentage of yellows. They actually have focus groups where they come up with different ratios of colors, and then they put them in a bowl, and then they just have people sit around and be like, what do you think of that bowl? And people are like, I don't like it. Too much yellow. Like they actually have focus groups, and they figure out, what assortment looks good to people. And that's how they kind of, I guess, come up with those ratios, which is weird to think about, but that's what they do. With the, so let's say you bought a bag of M&Ms, like a big bag, like a decent bag. I don't know how many are in such a bag.
You talking about sharing size or family size?
I don't know what this was.
It
was
has
like,
to be family, dude.
maybe it was like a big old, like, it looks like a purse. It looked like a bag.
Purse?
Yeah, it was like purse sized.
Like a suitcase carry-on.
That's definitely sharing size then. Brady wouldn't know about that.
Or like, like what horses eat oats in, like they just put it on their face and like,
It was that big?
yeah, it was big.
Dang, it's huge.
So I don't remember who that was, but so imagine you have a big bag of M&Ms like that, and let's say you want to you want to figure out what's the percentage of reds. And so, that's a good sample. That's a nice big collection of M&Ms from the factory. You want to know the percentage of red ones that the factory produces, the percentage that get made red in all the world. but you have your bag, so that's your sample. So you can find the percentage of reds in your bag, right? That percentage is what we call your proportion. We would call that, maybe I should draw it for you. Let me present. Oh, actually, let me check something. Yeah, okay. Which screen did I do? Can you see like my open math? Okay, good. I was drawing, but I'll get rid of them.
What was that?
I did like a perspective grid, and I was drawing people. I was bored. All right, so this is, let's say you have like the factory. You know, it's got all this smoke because they're making M&Ms. And then there's like a truck coming out. I don't know. You get the idea. There you go. So they make all the M&Ms, right? And they're coming out with a bunch of them all the time. The percentage of reds for the whole population is represented with the symbol, the lowercase symbol p, for categorical data. In your little, I don't know, your little purse of M&Ms, that percentage in your sample is p hat. And so your p hat, sometimes they call it your point estimate, which means your best guess at what p is, your best guess at what the true parameter is. It's your statistic though. And depending on your sample, you might get a different little p hat. So your percentage of reds would be your p hat, and let's say it's like, I don't know, 18%. So it's 0.18 in this case. Well, remember, like for quantitative data, let's say we had a mean value of, I don't know, 100, and there are numbers like 110, 90, 85, 105, I don't know. You've got numbers, and the standard deviation was like the average distance from the middle. So the average length, the average distance from the middle. That was what we called our standard deviation. And we could do that for X, for quantitative data. You could think of it as your difference from the middle. And the mean was just the average. It was the middle. So we could do that for quantitative data. For categorical data, and then from that we could build a normal distribution based on how wide the standard deviation was. We could place it at the mean, and we could build that normal distribution. For the sample, though, let me draw that line again. It's a little better. For the sample, we can only calculate the percentage that are red. And then what would the standard deviation mean? What would that be? Before it was the average distance from the mean. So the standard deviation for categorical data doesn't actually make much sense. Like just like the average, you can't really have an average. So the standard deviation, I was looking up why the formula is this. I knew at one point, and I kind of don't remember. I think I had figured out that it was basically just a guess, and you basically assume that you have the least amount of information possible. So I think it's just you go with the worst case scenario by default. I think I remember coming up with a way to explain it in that way, but now I don't remember how I did that. And I did a Google search, and my top results, they didn't really tell me why the formula was that. So I kind of don't remember how I figured that out. I'll try to figure that out again and then tell you next time why this is the formula. But the way we come up with a standard deviation for categorical data, like this is, with quantitative data, it represented the spread, sort of like the spread of the numbers. Well, with the fraction of reds, what the heck is the spread? What does that mean? Well, I'll get back to you on that, of why we come up with this formula specifically. But the thing that we use is you take your p-value, your I guess you call it p hat for your sample. You multiply it by, sometimes they call this q, but it is the complement of p hat. So if p hat was 10%, this would be 90%. It's just 100% minus p hat. So like if you have 30% reds, then your standard deviation would be 0.3 times 0.7 square root. If you had 25% reds, you would say 0.25 times 0.75 square root. But that is your standard deviation that you will use when you're trying to calculate a confidence interval for categorical data. So just to give you some numbers, let's say, how many do you think would be in that big bag of M&Ms? How many M&Ms do you think? It doesn't matter. Any guess?
$600.
Okay, we'll go 600. So my little n is 600. Let's say the number of reds, call that x, is, I don't know, 60. How about that? I'll make it easy. So our p hat would be 60 out of 600. That is basically 1 out of 10, or 0.1. Does that make sense? So in that case, our standard deviation would be 0.1 times 0.9 square root, which I don't know what that is. I'll calculate that in a second here. So I got square root of 0.3. So that's not great because that's kind of big. When you get closer to the edge, it's sort of not very good. Maybe I'll do slightly different numbers because, well, that's okay. We're fine with this. Okay, so I got 0.3 as my standard deviation, which again kind of doesn't make a lot of sense for categorical data. But let's say I wanted to make, what confidence interval do we want to make? Like 90%, 95? What do you guys want? 80?
95.
Okay. So we'll make a 95% confidence interval. We need to take our proportion, and we're going to say plus or minus on each side, a critical z-score for 95 times the standard deviation divided by the square root of the sample size, just like how we did confidence intervals with quantitative data. Well, now that we have a standard deviation defined for our categorical data, we can do the same thing. We're going to treat p hat as though it were x bar as our sample mean. So I'm going to say 0.1 plus or minus, and then for 95, I'm going to have to click 95% confidence. That's 1.96. So we will use that. The standard deviation we found to be 0.3. And then we're going to divide by the square root of the sample size, which was 600, because we had 600 M&Ms. So if I do that, I'm going to get 1.96, oops, I forgot the decimal, times 0.3 divided by square root of 600. That is 0.024. So that's my margin of error here. And so I would create a confidence interval. I'll do it in a different color, I guess, because I'm getting close to all my other writing, of 0.1 minus that number. So 0.076 to 0.1 plus that number. Well, that's going to be 0.124. So that would be my confidence interval for the percentage of M&Ms which are red. It would be between, if I said those as percentages, it'd be between 7.6% and 12.4%. That's my 95% confidence interval for a proportion. Does that make sense to you guys? Awesome. So I'm going to give you one, okay, to do, and then you tell me what you get. And let's see how that goes. I'll write that again. It's p hat plus or minus the critical z-score of the standard deviation over the square root of n. And for standard deviation, we're using p minus the complement square root. So let's say you have what should we be talking about? Skittles? I don't know. Let's say you have 300 Skittles. And let's say you have, what do I want to do? Purple ones? You have, I don't know, 57 purple ones. So you're going to need to find your p hat, which would be the 57 over 300. And that gives me 0.19. So remember, for 95% confidence, your critical z-score was 1.96. So why don't you guys give me your confidence interval for the percentage of purple Skittles in the world, given this information. Once you get it, let me know what you got. Anybody got it? You guys know what you're doing?
No.
Okay.
I went to the bathroom, grabbed some chips, and I came back, and I have no idea what was going on. So
You want to use this formula where this is your standard deviation.
Uh-huh.
You have your critical z-score. You have your proportion. And you have your sample size. So you want to make a confidence interval with the data that you have. So you just
What are we trying to solve? That whole left part?
Yeah, you're just making the
Oh,
confidence.
that's easy. That was easy.
You're just plugging things in.
I think I have it, but should I have two answers since I'm doing plus and minus?
Yeah, one will be with plus and one will be with minus.
Okay, do you want to know what I have?
Yeah.
Okay, so for the plus, I got 0.2299537238.
It's a little off from what I got, but that's kind of close. We'll go through it. What's your other number?
0.150.
Okay. I think you got a slightly
I think I
smaller.
did something wrong.
Maybe I did something wrong. We'll check. How about you, Maddie?
For my plus, I had 0.234.
That's what I had. Yeah.
Me as well.
Good.
And then for my minus, I had 0.1456.
Yeah, that's what I had. Yeah. So I'm guessing you might have done something slightly wrong, Jordan, but you're pretty close actually. Yeah, I had about 14.6%, between 14.6% and 23.4% as my confidence interval for 95% confidence. What did you do,
Wait, what'd you guys get?
0.146 about to 0.234. What'd you get?
0.2343.
Yeah.
for the plus.
Yep. That's what we got. So I just put in like the 0.19.
So that was the answer.
That was that's the high end. We're doing a confidence interval, so we want an interval. So it's going to be 1.96 times the square root of 0.19. And then what's 1 minus that? I'm using my calculator stupidly. 0.81 all over 300. If you do that, my margin of error was about 0.0444 about-ish. And when I added and subtracted, I got about, my interval was 0.146 to 234. I went to 3 decimal places. Well, I went to 4, but then I rounded. Are you guys okay with that?
Where did you get the 0.81 up there for this?
It's 1 minus p. So your
Oh,
p is 0.19. So just 1 minus that gives you the complement.
Can we put like, and when we're doing it in our calculator, can we do 0.19 and then do times 1 minus 0.19 and will it still give us the same answer?
Yeah, if you do parentheses, that is actually what I did. That's why I had to just now because I didn't do it before.
Okay.
Any questions on that? All right, like I said, I should have made an assignment for you. I don't know why I didn't. But next class, I guess I will have one. We'll go over these steps one more time next class, and then you'll have like an assignment with it. Does that sound okay?
Yep.
Sounds perfect.
All right. Well, you guys are free to go, I guess. You guys have a great
Awesome.
weekend.
You
I'll
too.
see you Tuesday, right?
We'll see you Tuesday.
I'll see you in a
Bye,
minute.
Aiden. Bye, Aiden.